Okay, so let's continue where we left off. So the next section is 4.5.5, which is the Poisson distribution. Okay, so the Poisson distribution can approximate the binomial probability function when n is large and p is suitably small. So the Poisson distribution can approximate the binomial probability function when n is large and p is suitably small. Okay, so definition 4.7. And so what I need to define for you is what the Poisson distribution is, right? So that's what the section is about. So let lambda be a positive upbeat constant. Okay, the function p of x lambda is equal to lambda to the x, e to negative lambda, over x factorial for x equals 0, 1, 2, 3, dot, dot, dot. That function is the Poisson probability function. With parameter lambda. Okay, and so it depends on x and lambda. There's two parameters. Okay, so that's the definition of the Poisson probability function with parameter lambda. Also, note a Poisson, a random variable with Poisson probability function is called a Poisson random variable. Okay, so that's explaining what a Poisson random variable means. So you start with a random variable and you give it the Poisson probability function. Then a random variable with the Poisson probability function is called a Poisson random variable. Okay? Alright, so that's the definition of the Poisson probability function. If you have a random variable with that function, you can then add the word Poisson in front of it, and it's now more specifically a Poisson random variable. And this probability function can approximate the binomial probability function we discussed earlier. And so that function, right, the binomial probability function, that function was the function h, x, and p from earlier. And not h, b. X and p from earlier. Right, it's probability that in n Bernoulli trials, x are successes with a probability p of success in each trial is little p. Okay? And that was without replacements. With replacements, right? So we replace it, so each time we conduct a trial, each trial is the same, independent of what happens in any other trial, right? So there's a total of n trials that you want to find the probability of x successes in x trials with a probability of success in each trial is p. That's the binomial probability function. And so you can find the value of that by finding the corresponding value of the Poisson probability function. And so this function will approximate the value of that one. And same the other way Okay? And that's when little n is large and little p is suitably small. Right? And so if this little n is large enough and this little p is suitably small, if this is suitably smaller, much smaller than this, then this probability is approximately that one. Okay? Okay. Let's go. Okay, so summary, if little n is large, and little p is small, so if little n is large and little p is small, so that lambda equals np is moderate, then the binomial probability is approximately the Poisson probability. Okay, that's the summary. So if little n is large and little p is small, so that lambda equals np is moderate, then these two approximate the same. Okay, so this is a good thing to focus on here because I realize that's difficult. And so focus on what I'm saying here. It's a summary of it, right? And you should know what the values of each of these probability functions are, right? So again, this one is n choose x p to the x 1 minus p, which is q to the n minus x. Usually you would think of this as q. It's the same form. That's q, right? But I'm using p only, so that would be 1. And then this one, again, is lambda to the x e to the negative lambda x over x factorial. Sorry, e to negative lambda. Okay? Okay, so this is the Poisson probability function. This is the binomial probability function. And they're approximately the same if little n is large and little p is small enough. So if this little n is large enough and that little p is small enough, so that lambda, which is n times p, which we use here, is moderate, and they're approximately the same. Okay. Right, so this thing's very large, this thing's very small, their product is moderate size. Then this probably is approximately the same size. That's a summary so far. And so this is a bit difficult at this point, and so this page is a good page to focus on when you're trying to understand the Poisson probability function and how it approximates the binomial probability function. Okay, so when you're studying, focus on just this summary of what I wrote on this board here. Okay. Okay. And at some point, some given amount of time, focus on this board. Okay? And then okay. Okay, so that's a summary of so far of this topic. So let's look at example 4.15. Okay, so if the probability is 0.0001 that any one passenger in a subway train, I'll just write train, is robbed, will be robbed. What is the probability? Doesn't seem like a safe train. What is the probability 10 of the next 50,000 passengers? Someone told me that, I won't go on the train. So what is the probability 10 of next 50,000 passengers will be robbed? Use the Poisson approximation. use the Poisson approximation of the binomial distribution. I'll assume you laughed at my jokes. Okay, so if the probability is 0.0001 that any one passenger in the train will be robbed, what is the probability 10 of the next 50,000 passengers will be robbed? Use the Poisson approximation of the binomial distribution. Okay, so solution. Excuse me, sorry. Okay, so the solution to the problem. So we want to use, the goal is to use the Poisson approximation of the binomial distribution. Right? And so that lends itself to thinking, well, somehow we're associating the probability, you should be thinking of the probability as a binomial distribution, right? Because somehow we can translate this probability into into using the binomial probability function. And so let's find what the probability function is that gives you this probability, and then let's find the Poisson probability that approximates that probability. And then by calculating that one, we'll have approximated the actual probability. Okay? So step one, let's find what binomial probability B of x and p would give you the answer. Okay, let's find what binomial probability would give you the answer to this problem. Step two will be approximating that with the Poisson probability. Okay, so let's do that. So what obviously stands out to me is that the probability is 0.0001. That's the first thing it says. So the probability of success is going to be that. Okay. Little n is the number of passengers. So 50,000 passengers. Right. So each trial will be whether or not each passenger is robbed. X is going to be the number of successes. So 10 will be robbed. So a success here is being robbed. Okay, so if someone gets robbed, this is a success in this situation. Right? So again, a success is not something good happening. It's just a desired outcome happens. And so in this case, what we want is for someone to be robbed. And so, 10 people being robbed means 10 successes. Okay, so there's 50,000 passengers. We want 10 people to be robbed, and the probability that any one passenger will be robbed is 0.0001. So let those values, let little p be that and be that x be at. Then the binomial probability that describes this probability is equal to b of 10, 50,000 and 0.0001. Okay. Right. So step two, find the Poisson probability x lambda that approximates b of 10, 50,000, 0.0001. Okay, so if you follow these two steps, it can be simple. Okay, first we found what function represents our probability using the binomial probability distribution, and now we're going to find the Poisson probability that approximates that. Okay, so the Poisson probability x lambda, which is approximately, the actual probability is the binomial probability, which is 10, 50,000, 0.0001. That's approximately the same as the Poisson probability with primary lambda. Okay, So now we want to find the value of our Poisson probability. We know x is 10, right? X is 10 right here. So that's 10, but what's lambda? So what is the relationship? So lambda is NP. So lambda is n times p. That's the number of passengers that are going to board the train, and p is the probability that someone will be robbed. The probability someone's robbed. So it's 50,000, number of people that go into the train, times the probability that someone goes in the train is robbed. So in a way, that's like the average number of people you'd expect in the next 50,000 passengers to be robbed. And so 50,000 times 0.0000.0001 is 5. So lambda is 5. And so because little n is large enough and little p is small enough, and their product is of moderate size, lambda is 5, right? So there's 3 conditions we have to check. In order for this claim to be true, that they're approximately equal, the binomial probability and the Poisson probability, 3 things we have to check in order to make that statement. 1, that lambda is large enough. Okay, lambda has to be large enough. 2, little n has to be large enough. P has to be small enough. Okay, so n has to be large enough and little p has to be small enough. And so what we say is that if the probability is at most 5% of the value of little n, you're good. Oh no, sorry. So the so little n is large enough and p is small. Yeah, that's good. Okay, so I'm thinking of the hyperbolic. Okay, so little n is large enough, little p is small enough. That's good, and lambda at 3, lambda equals np is moderate. Let's check to that also. Okay, so those are the 3 things we need in order to say that the binomial probability is approximately the Poisson probability. Little n is large enough, 50,000, good. Little p is small enough, 0.0001, that's good. And lambda equals np is moderate, lambda is 5. So that all 3 of those check out, and so the binomial probability is approximately the Poisson probability. That's the Poisson probability where x is 10 and lambda is 5. And so lambda is 5. And so you just plug that into that probability function, right? And so remember, I'm going to put that here. This is separate from that. The Poisson probability of x lambda is equal to lambda to the x, e to the negative lambda over x factorial. Okay, so it's a strange probability function, but if you follow the rules that we set up, you can use it to make some conclusions and to find some probabilities, okay? So it's a matter of remembering the strange function and knowing the rules for using it, and then you can use it to find the probability of some weird situations happening, okay? And so the probability of that is, so lambda is 5, so that's 5 to the 10th power times e to the negative 5th power divided by 10 factorial. Okay, and so when you calculate that, use your calculator, you get 0.018. Okay, so the question is, what is the probability 10 of the next 50,000 passengers will be robbed? And it's 0.0181. And so it's a little less than 2%. So a little less than 2% chance that 10 of the next 50,000 passengers will be robbed. That still doesn't sound safe. Okay, and so that's the answer to that problem. And let's continue. Okay, I'll leave this on. remote so you can see. Right? So this is an important point. This part where I approximate the Poisson probability, approximate the binomial probability with the Poisson probability, right? The justification for that are these three things that I know. From studying the problem, I know n is large enough, p is small enough, and lambda equals np is a moderate size. Those things allow me to conclude that those two probabilities are approximately the same, right? And the probability in the original problem is this binomial probability, the value of that binomial probability. But there's a lot of instances where calculating this is very difficult, and so it would be much faster and easier if instead of calculating this, you find this, which is approximately that. Okay, so we saw in a previous example in a different problem where the values of these two probabilities were the same to the first 3 decimal places. So it wasn't until the 10,000th digit, the 10,000th place, where these two probabilities were different in that other situation. And so we saw an example of how these two things can be very close. Okay, and so in this case, so you can hopefully believe that the probability we computed with this weird function is approximately the same as if you calculate that thing. Okay, let's keep going. Okay, theorem 4.2. Theorem 4.2 is Poisson's limit law. So Poisson's limit law, if p varies with n, so that p equals lambda, where lambda is positive, constant, then the limit as n approaches infinity the limit as n approaches infinity of that binomial probability is equal to the Poisson probability of x lambda. Okay, so p varies with n, so that np equals lambda, where lambda is positive, constant. Then the limit of the binomial probability is equal to the Poisson probability. Okay, and so actually this is so this makes it more believable that this probability that these probabilities would be approximately the same, because if lambda equals np and the limit as n approaches infinity of this is that means if n gets really, really large, then you should be getting this thing to be very close to that thing, right? When the limit of something is something else, that means that as this thing gets closer and closer to, say, infinity in this case, as this gets larger and larger, this thing should eventually be getting closer and closer to p. Okay? Okay, so that's that. So underneath that are examples of random phenomena. With Poisson distributions. Okay, so examples of random phenomena with Poisson distributions. The number of incoming calls, within a fixed interval of time, at certain switch points. So this is an example of a random phenomenon with a Poisson distribution. The number of incoming calls within a fixed time interval at certain switchboards. So these are strange, but we'll see later how this works. Here's another example. In the book, this is the fifth example. The number of fish caught in a day in a certain region. Okay, so the number of fish caught in a day in a certain region, that would be a random phenomenon with a Poisson distribution. And this is example 11 in the section. The number of emergency patients on a given day in a certain hospital. Okay, so the number of emergency patients on a given day in a certain hospital, that's also a random phenomenon with a Poisson distribution. Okay. Okay, and so, so we have that probability where the limit of the binomial is the Poisson. And so let me just make a note here. So some random variables, which I'm doing in VAR, some random variables are essentially binomial. Are essentially binomial random variables with large little n and small p. Hence, they are essentially Poisson random variables. Okay, so note some random variables are essentially binomial. So some random variables are essentially binomial with large n and small p. Hence, they are essentially Poisson random variables. That's because a binomial value of binomial probability function is approximately the value of the Poisson probability function when n is large enough and p is small enough, right? And so when you have a random variable that's essentially binomial with large n and small p, then they're essentially a Poisson random variable. Okay. Okay. So let's look at another example. Okay. And this will illustrate. Okay, so this is example 4.16. So let x equal the number of misprints on a page selected at random. From a large book. Explain why it is reasonable to to assume X is a Poisson random variable. So example 4.16, let X equal the number of misprints on a page selected at random from a large book. Explain why it is reasonable to assume X is a Poisson random variable. So let X be the number of misprints on the page. Okay, so let's suppose each page has little n letters or other symbols. Okay, letters / symbols, right? So there's just little n symbols on each page. That's the assumption. Okay, so if an error in a symbol on the page is a success in a Bernoulli trial of probability p less than 0.1 and little n is greater than 100, and capital X is the number of successes in those little n Bernoulli trials, then the probability that capital X equals little x is equal to the binomial probability of X successes out of n Bernoulli trials, where the probability of success in each trial is little p. Okay, so let me explain this. Right? Okay, so we're going to suppose each page has little n letters or symbols. Okay, so we're going to take every page in the book to have the same number of pages. We're going to make that value little n. If an error in a symbol is a success in a Bernoulli trial of probability p less than 0.1, meaning we're saying that the chance that the person who made the book, there's a probability of less than 10%, less than 0.1, that any individual symbol was printed wrong. Okay? And we're going to assume that the number of symbols on each page that we made little n, that little value, that little n, is greater than 100. Okay? And so these are reasonable assumptions because it's reasonable to assume that there's more than 100 characters in a page, and it's reasonable to assume that the probability of an error on each character is less than 10%. Okay, and let X equal the number of successes in those n Bernoulli trials. So X is the number of errors in a page, right? Because each letter either was printed wrong or correctly. A success is when it's printed wrong, and so X is the number of errors on the page. Okay, then the probability that the number of errors on the page is some value little x is equal to the binomial probability, the value of that function, where little x is the number of errors, n is the number of letters on the page, and p is the probability of an error in that page. Okay? Okay, so since little p is less than 0.1, which means little p is small enough, and that little n, which is greater than 100, means little n is large enough, and lambda equals np, so it's n times p, so alright, yeah, so I guess we're just approximating it. So that'll be a moderate size, because if you look at 0.1 times 100, it'll be 10. And so n can be larger and that can be less. So we don't know the exact value of lambda, so, but lambda is okay. So since p is less than 0.1 and is greater than 100, we can assume that the probability of getting x errors, little x errors on the page, which is this binomial probability, right? That it can be approximated by the Poisson probability, where lambda equals NP. Okay, so we can assume capital X is a Poisson random variable. Or it's essentially a Poisson random variable. So we can assume X is a Poisson random variable, right? And by assuming that, that means, remember the meaning of saying something is a Poisson random variable is that its probability function of that random variable is that little p, the Poisson distribution, right? And so we can assume it's this type of variable with this probability function because the binomial one that describes it is approximately equal to it. Okay, and so that answers the question. Explain why it is reasonable to assume X is a Poisson random variable. Okay, because we can assume it's a binomial. We can use the Bernoulli function to describe the situation, and that's approximated by the Poisson distribution. Okay. I guess I'll leave this up for a moment so you can look at it. Okay. You can always watch this video again, and so if you're getting stuck at this point, you can watch the video again, right? So this is a bit more difficult than previous lessons. I feel like the Poisson part gets more trickier. The binomial part was difficult, was this kind of a step forward also, and I think this is another jump a little bit in the subject to understand the Poisson distribution. So you might want to focus on, spend some time understanding this, and it's okay if it takes a while to get. It's more difficult than the previous material. Okay, keep going. Okay, 4.5.5.3, Poisson processes. Okay, so 4.5.5.3, Poisson processes. And so what this is explaining what a Poisson variable situation will look like. So a physical process, if a physical process satisfies three conditions, then the random variable X that represents the total number of occurrences of this phenomena within the fixed period of time / space. So you could be talking about a fixed period of time or a fixed amount of space is a Poisson random variable. Okay, so if a physical process satisfies three conditions, then the random variable X that represents the total number of occurrences of this phenomena within the fixed period of time / space is a Poisson random variable. Okay, and so we're going to list now are those three conditions. And so if you're looking at a physical process that satisfies these three conditions, where X is the total number of occurrences of some phenomena within some fixed period of time or space, then your X is a Poisson random variable. Okay. the first condition. The number of occurrences of the phenomenon in any two or more disjoint intervals of time or regions of space. It's important to point out or regions of space because the problem might be dealing with space. Must be independent of each other. Meaning when you look at one interval of time and a completely separate other interval of time, a disjoint one, then the number of occurrence of the phenomena in each of those disjoint interval times, neither one depends on the other. And so when you look at one interval and you look at a completely other disjoint interval, what happens in those intervals are independent of each other. They have no effect on what happens in the other interval. Okay? Okay, and so you could, instead of two, you could say two more. You could say three. If you had three completely separate intervals from each other, if you looked at any one of them, what happened in the other two would have no bearing on how many times the phenomenon occurred in the interval you looked at, you chose. Okay, so that's part one. Each interval is independent of any other disjoint interval time, and same goes for space. If I took three different regions of space that were disjoint, separate from each other, and I looked at, well, how many times does this phenomenon occur in one of those spaces? It would have no bearing on what happened in any of the other regions of space. Okay, that's part one. Two, the probability of at least one occurrence of the phenomena during any subinterval of length 1 over n is always the same. Okay, so what does that mean? So for instance, if you're thinking about telephone calls you receive and you ask yourself, so if let's say n was 5, right? So let's say you want to know how many phone calls you would get in 1/5 of an hour, right? Then no matter where you looked, so if you looked at an hour period and you said how many phone calls, what would be the probability of getting at least one phone call in 1/5 of an hour, which is 12 minutes, right? So you'd say, if I chose this length of 12 minutes, what would be the probability of getting at least one phone call there? And that 12, it's an interval. So I can't divide those 12 minutes there together, those 12 minutes, right? I can't take that 12 minutes and put 6 of them here and 6 of them somewhere else, right? It's a total of 12. So you have the hour and you take 12 of those minutes that are together, continuous 12 minutes, and you say, how many phone calls what's the probability I get at least one phone call during those 12 minutes? And then I take a completely separate interval of 12 minutes. It could overlap those 12 minutes, or it could be completely different from those 12 minutes. If I consider another interval of 12 minutes, then the hour, it being also 1/5 of an hour, that would mean the probability of getting at least one call in those 12 minutes would be the same. That's what this is saying for that situation, okay? It doesn't have to be an hour, it doesn't have to be phone calls. It's just whatever the situation is, whatever the phenomenon you're talking about, there the phenomenon would be receiving the phone call during that hour. The phenomenon would be getting a phone call. But okay, that's an example of that. Okay, so continuing to, also if P sub n is the probability of at least one occurrence of the phenomenon during any 1 over n length interval, then there is a constant lambda positive such that the limit as n approaches infinity of n p sub n is equal to lambda. Okay, and so, right, p sub n is the probability, if you let p sub n be the probability of at least one occurrence of the phenomenon during any 1 over n length interval, then there is a constant lambda greater than 0 such that the limit as n approaches infinity of n times p sub n is equal to lambda. Okay, so if you take your starting interval, right, and you take 1 over nth of that, 1/nth of that, if you take the limit as n approaches infinity, that length is going to 0, right? But every time you have that length, smaller and smaller length, you have the probability associated with the probability of the phenomenon occurring at least once in any subinterval of that length. And so 1 over n is tending to 0, but each of those lengths has a corresponding probability, right, of at least one phenomenon occurring in any subinterval of that length, 1 over n. And so when you take the probabilities, those probabilities, and multiply them by n times p sub n, as n gets larger and larger and tends to infinity, that sequence of values will approach lambda. So you could do 1 times p sub 1, 2 times p sub 2, 3 times p sub 3, 4 times p sub 4, 5 times p sub 5, dot, dot, dot. That sequence will tend to lambda. So as n approaches infinity, that sequence will tend to approach the value of lambda. That's condition 2. Okay? That's condition 2. Right? And so these are the 3 conditions that, when satisfied, means that a random variable x that represents the total number of occurrence of a phenomenon within a fixed period of time / space is a Poisson random variable. Okay, these 3 conditions. So I'm going to have to erase this part, and so here I'm going to put the 3rd condition. Okay, and so this is where I'm going to put the 3rd condition. So I'm actually going to erase the title also. I need a lot of space here. So condition 3, the probability of 2 or more occurrences in any given very short period of time short interval of time. You need to be exact about the fact that an interval of time must be smaller than the probability of just one occurrence. There. Okay. The same place. Same interval, region of space. Okay, so the probability of 2 more occurrences in any given very short interval of time must be smaller than the probability of just one occurrence. Meaning, if you take, let's say you had an hour, you thought of an hour, and you said, well, how many calls can I expect to receive in 10 seconds? Any interval of like 10 seconds in an hour, right? Then, right, no matter which 10-second interval you choose, you'd expect the probability would be the same for the number of calls you expect to receive, right? This is saying that if you were to say, well, what is the likelihood that I receive 2 phone calls in those 10 seconds? What should happen is that the probability of receiving 2 phone calls in those 10 seconds should be less than the probability of receiving just 1 phone call. It should be less likely that we receive more phone calls than fewer phone calls, right? And so that applies to 2 or more, right? And so if the probability of receiving 7 phone calls in 10 seconds is also less than the probability of receiving just 1 phone call in those same 10 seconds in the whole hour, right? That 10-second subinterval of an hour. Okay, and so that's assumption 3 so far, and in addition to that, plus in any given sufficiently small length interval of time, the probability of 2 or more occurrences must be about, so the probability of 2 or more occurrences. So it's not just the number 2, it's 2 or more. So the probability of 2 or more calls in those 10 seconds is less than the probability of just one phone call. Okay. Okay, so that means the probability of receiving 2 phone calls, or 3, or 4, or 5, or 6, or ... The probability of the union of all those is less than the probability of receiving 1 in those 10 seconds. That's what that means. Okay. So plus in any given sufficiently small length of time, the probability of 2 or more occurrences must be about the same as probability of just one occurrence. Okay, so this is you might find this either very weird or making complete sense, right? So what this is assuming is that the probability of 2 or more occurrences of the phenomena in your very small length interval, that probability is less than the probability of it happening once, but it's also very close to it. And so this whole thing in total is saying, that the probability of the phenomenon happening 2 or more times in a sufficiently small interval is close and less than the probability of it happening once. Okay? So the probability of it happening just once is less than, but very close to the probability of happening 2 or more times. Okay, so that's the third condition. So this is condition 1, condition 2, and condition 3. Okay, so maybe you want to write these down, or hopefully you've been writing them down. And so these are the 3 conditions. Okay. Okay, so I'm going to erase 1 and 2. And I'm going to keep the third condition there. It's at the top. And so I'm going to continue below that because there's more to say. Okay. So those are the 3 conditions. But now I'm going to conclude that if the 3 conditions are satisfied, so if the 3 conditions stated are satisfied, there is a constant lambda greater than 0 such that for each given value of t, the distribution of x sub t is a Poisson distribution with parameter lambda t. That is the probability that x sub t is equal to little x is equal to lambda t raised to the x times e to negative lambda t divided by x factorial for x equals 0, 1, 2, 3, and so forth. Okay, so if the 3 conditions that I stated, those 3 conditions stated are satisfied, there is a constant lambda greater than 0 such that for each given value of t, the distribution of x sub t is the Poisson distribution with parameter lambda t. And that is, you get this equation. Okay, so this is the probability that the number of occurrences of a phenomenon occurs in some length t interval, some fixed length t interval is equal to little x. This is the probability that the phenomenon you want to observe happens little x times in a fixed interval of length little t. Okay, the probability of that is equal to, that's represented by the Poisson distribution with the parameter lambda t. And so normally, the Poisson distribution x lambda would be lambda to the x e to negative lambda over x factorial. Right? So the Poisson probability distribution with x and lambda as parameters would be lambda to the x e to negative lambda over x factorial. This is the Poisson distribution with parameter lambda t. And so instead of lambda being your parameter, it's lambda t. And so the value of this function, where instead of saying lambda, you say lambda t, you would substitute lambda t there. So it would be lambda t raised to the x power times e to the negative lambda t now, divided by x factorial. That's what that is. Okay? So it's the Poisson probability function, but instead of lambda as your parameter, it's lambda t as your parameter. And so instead of lambda here, it's lambda t, that's x. Instead of lambda here, it's lambda t, and there's still x factorial. Okay? And so that's what that means. It means that if those three conditions are satisfied, there is some constant lambda greater than 0, such that the probability of your phenomenon occurring x times in some fixed interval of length little t is equal to the Poisson probability function, whose parameter instead of lambda is lambda t, which is this or that. And this is for any values of x, 0, 1, 2, 3, and so forth, where x is a non-negative integer. 0, 1, 2, 3, and so forth. Okay? So that's the conclusion of what happens when those three conditions are satisfied. Okay? And important to note, it says there is a constant lambda positive. It doesn't tell you what that constant is. Not here, right? And so with just this, you know there is some value of lambda, where if you wanted to know the probability that your phenomenon occurred little x times a fixed interval like little t, the probability that occurring would be this, but for some constant lambda positive. And so you need to be given that constant lambda positive or find it. And so once you have it though, you plug it in, and now you have the probability in terms of the parameter little x, right? You need to be specified how many times you want that observed phenomenon to occur in order to know the probability of it happening that many times. Right? Okay? Okay. So, and you can choose the value t whatever you want, right? For each given value t. So for each value t, there would be a corresponding constant lambda greater than 0 you would use to get that probability. And so let's say t was 5 for some reason. If t was 5, there would be a corresponding constant lambda positive which just says that exists. And so if you had or was given the lambda for t equals 5, you could use it to find the probability. Now, if instead you chose t equals 2, if instead you chose intervals of length 2, then the old value of lambda would not help you there. You would need to be given a new value of lambda corresponding to that new value of t that you would plug in here to find the probability of that. Okay? So for each value of t, there is a corresponding positive constant lambda you use here to find this probability. Okay? And so a lot of problems will give you the value of lambda, and they'll say this is a Poisson process with lambda equal to this, right? Or, you know, some problems will be, it might be given directly from you, or you can deduce what lambda is. We'll see. Okay, that. Okay, and so that's important. And so focus on this also, white box right here. Focus on that, the three conditions, and especially this function. Okay, know why this is a Poisson distribution with parameter lambda t, right? This is the Poisson distribution. This is the Poisson distribution where instead of lambda, you use lambda t. focus on this board also. Okay, let's keep going. Okay, so you're going to want to spend some time on this video. Okay, so example 4.19. The number of telephone calls arriving within a time interval blank t in minutes is a Poisson process x sub t with lambda equals to 2. A, find the probability that x sub 5 is equal to 0. Okay, this is the probability that no telephone calls arrive during a given 5-minute period. Right, so the length time is fixed, and so this is the probably x of 5 is equal to 0. The observed phenomenon is a telephone call, right? X is the number of telephone calls you receive, the random variable. And saying that it's equal to 0 means you're thinking of receiving 0 phone calls. And then the subscript 5 means it's the fixed interval time. And so this is no telephone calls received in any 5-minute interval. Okay, so you have to consider some interval of time or some region of space. So here we're considering an interval of time. Okay, so let's just remind ourselves what the value of p of x sub t is equal to little x is. That is lambda t to the x e to the negative lambda t over x factorial. Okay, right, so it's a Poisson distribution function where the parameter is lambda t. And so then that's equal to, well, lambda is 2. So it's 2, and now, so I'll put 2t here. 2t to the x, e to the negative 2t over x factorial. This is where lambda, I'm using the fact that lambda is 2. I'm not multiplying this on the side, I'm just saying lambda is 2 from here. Okay, and so that means that the probability of no telephone calls in 5 minutes So the probability of receiving no telephone calls in 5 minutes is the probability that x sub 5 is equal to the 0, where x is the number of telephone calls you receive, right? So you expect to receive 0 telephone calls in a 5-minute interval length of time. P of x sub 5 is equal to 0. And so what is that equal to? That is equal to, well, now t is 5 and x is 0, right? This is the t here. T is 5 and little x is 0. So here little t is 5 and little x is 0. And so it's here. So 2 times t, which is 5, raised to the x, which is 0, times e to the negative 2 times t, which is 5, divided by x, which is 0 factorial. 0 factorial is 1. So I already mentioned that in another class. I'll remind you, right? When you see 0 factorial in the denominator, you're thinking, how could you have a 0 in the denominator? It's fine, because 0 factorial is 1. Okay, so 2 times 5 to the 0 is 10 to the 0 power, which is 1. That's fine. 0 factorial is also 1. Both none of those matter. E to the negative 2 times 5 is e to the negative 10. And that's it. That's the value. Okay, and let's write it as a decimal. This is e to negative 10, and which is equal to 0.000045. Okay, and it keeps going. It's an infinite non-repeating decimal, so you can keep going after those 6 digits, but I'll stop there. Okay, so e to the negative 10 approximately is 0.000045. Okay, so that's part A. Find the probability x of 5 is equal to 0. Okay, so let's do part B of this example. Part B, find the probability of x sub 1/2 is greater than 1. And that is the probability of more than one call, more than one telephone call, in a half-minute period. Right? Okay. So this is right. X, which is number of telephone calls, is greater than 1. So you receive more than one telephone call, and this is the time interval length in half a minute period. So that's what we want to find. Probably more than one phone call in a half-minute period. So P of x sub 1/2 is greater than 1. It's equal to 1 minus the probability of the complement of that. And so that's the probability that x sub 1/2 is less than or equal to 1. And what does that mean? That's 1 minus the probability of x sub 1/2 is equal to 1 minus the probability of x sub 1/2 is equal to 0. All right? X is the number of telephone calls you receive. You can't receive negative telephone calls. And so if you want to find, thinking of the number of telephone calls being less than or equal to 1 means either there's 1 or 0 telephone calls you're receiving in a half-minute period. Okay? So the probability that x sub 1/2 is greater than 1 is 1 minus the probability of x sub 1/2 is less than or equal to 1. That's 1 minus the probability x sub 1/2 is 1, minus the probability x sub 1/2 is 0. Right? It's plus, but then I distribute the minus sign, and so they're both being subtracted. Okay, so let's continue. And so now this is 1 minus this probability, which is 2 times 1/2 raised to the first power times e to the negative 2 times 1/2 over 1 factorial minus 2 times 1/2 to the 0 power e to the negative 2 times 1/2 over 0 factorial. Okay, and so the lambda t, right? So lambda is 1/2 and lambda is 2 and t is 1/2. So lambda t to the x, here it's x is 1, e to negative lambda t over x factorial. New values, lambda is still 2, lambda is 2, t is 1/2, lambda t to the x, which is now 0, e to negative lambda t over x factorial, which is 0 factorial. This is 1 minus e to the negative 1, because this is, everything else is 1, so it becomes e to the negative 1, minus, that's also 1, and so you get e to the negative 1. So it's 1 minus e to the negative 1 minus e to the negative 1, which is 0.26424. Okay? And so that's the probability that the number of telephones you receive in any 1/2 minute length interval is greater than 1. 0.26424. Okay? And so that's example 4.19. Okay? Good. Okay, and so 4.5.5.4 is about the parameter lambda. And so if the value, which is a number value, the value slash number of an experiment is a Poisson random variable x, and if the experiment is repeated a number of times, we expect the average of capital X to be lambda. Okay, so lambda is kind of like the average here. So if the value or number, the value slash number of an experiment is a Poisson random variable X, then if the experiment is repeated a number of times, we expect the average of X to be lambda. Okay, so lambda is like the average here for a Poisson random variable. Okay, so we'll stop there and I'll see you next time.